Okay, my presentation is on vector fields, kind of what they are and their applications. I guess to start off, a vector, I mean if you're not familiar with the term or if it's been a while, a vector is just a quantity like displacement or velocity or force that has a magnitude and direction. And we'll show an example of that in a little bit. Some other notation that I use quickly. I and j are just basic standard vectors, like unit vectors. Like I is 1, 0, j is 0, 1, and we'll see k, that's in 3D, 0, 0, 1. But a vector field, if you look, is a vector function with inputs x and y. That is equal to your scalar functions, p and q, times those that I and j, your basic vectors. You can also use the sideways brackets, kind of the greater than or less than looking signs, as a notation for vectors as well. I think that's more commonly how they're familiar to us. But simplified, your field or function is equal to that scalar function times I plus the q function times j. To plot a vector field, I made a little table here for that vector function negative y, I, plus xj. And if you look at the point on the left there, your x and y points, what you do to plot the vector is you take, for this function, your negative y vector. So look at the point 1, 1 here. Your negative y value would be negative 1. Put that right there, then just bring your x over. So I mean, you're not changing the sign of x, you're just negating the y is basically what that means. You take a look at negative 2, 1 towards the bottom, that would translate to negative 1, negative 2 for your vector. And what that really means, I mean, this is just a few examples, but if you plot that, that is your vector field. I mean, scaled from negative 2 to 2 on the x-axis, negative 2 to 2 on the y-axis. And you see it's kind of a counterclockwise circle. And I'll touch briefly on the magnitude. If you look at that very top left vector there, that's what each arrow is, by the way, a vector for that given point. We'll look at the point negative 2, 2, which is where that vector is really nearby. You'll notice that it is a lot more pronounced, bolder than maybe some of these vectors. Well, that has a magnitude that is greater than, say, the point negative 1, 1. I mean, it's the same direction because it's the same values. I mean, it's a similar value to the function, just twice as big. So, I mean, that's kind of what the arrows, and that'll show up more in my examples later on. And here's some more examples, kind of to help you see that in terms of magnitude. We'll look at x cubed plus y squared. You have, well, I mean, even think about it. You take a value less than 1 and plug that in, like a point, and plug that into your vector function. You're going to get a very small magnitude because you're exponentially, it'd be decreasing for a fraction. So the magnitude is definitely smaller than, say, you plug 2.22, it's going to have a greater magnitude, for sure. And that just increases as you move along. I mean, 100, 100, you can think of the magnitude in that in comparison. Just another example, you can kind of see that for sine of x plus tangent of y. So if you recall, that was the equation we had for vector field in 2D. Well, 3D is just basically the same thing with x, y, and z inputs. And you have your r scalar function times that unit vector k. And an example of that, I apologize, the picture's kind of not the best to really see. It's actually the same picture, just rotated. I labeled the axes so maybe you could get a better glimpse of what it's actually doing. For that vector function, I just threw in negative x plus y minus z. I mean, so great. We can make some cool pictures. I mean, you can plot all kinds of vector fields, but what's the applications? I mean, what is this? What do you use these for? Well, there's quite a bit. I mean, especially modeling wind pattern velocity, water current, gravitational fields, electrical fields. take a look at a couple examples here. A magnetic field, for instance, you take any direction coming off the North Pole, you can see that it translates to that spot on the South Pole. That's a little more realistic representation of it. Map of wind velocity for January 2005. I think in this case they were looking at the Brazil area. If you didn't notice right away, North America, South America, grays are landmass. But if you look, this kind of reinforces what I mean by magnitude. The wind speed, you can see that the darker purple is a higher wind speed in meters per second. We'll look at the darker spots compared to the lighter spots. Those arrows are the direction of the wind, but they also show the velocity, and that the stronger arrows obviously have a higher velocity compared to, say, in that area there, the lower wind speed relates to that smaller arrow. You can see that. Gravitational force of Earth. I wanted to get a really great 3D model. I couldn't find it, but this 2D one, you see Earth in the center there, with the center of Earth at the origin. You notice that the gravitational force, which is what each of those vectors are at a given point in space, is attracted to the center of Earth. Now in a 3D model, if you can imagine that cube, all of those arrows would be pointing towards the center of Earth. I mean, that's a basic gravitational field. It's a lot darker on that screen. This is Hurricane Isabel at a certain point from 2003. I don't know if you remember that. It hit the northeastern part of Florida. But if you can look, you can clearly see at least these arrows there. They're kind of going in that negative y plus x direction that we saw earlier. But what it's showing is the velocity at a given point and the direction. And there was an animated picture of this, and it kind of moved off north and east into the kind of northern Jacksonville area. And that's what that's showing. I mean, basically, vector fields they're useful for modeling. Like I said, wind speeds, migration patterns, and all sorts of models in physics and biology especially.